Yeah, we're gonna switch gears a little bit. And so if people didn't follow like the previous dynamical code, subsystem codes, all of that stuff, we can still jump back in because I'm gonna introduce everything from the beginning, except like some of the QEC stuff that Kishore talked about in the very beginning. Yeah, so even like before beginning the actual presentation, I have this section 0 on what bosonic coding actually really means, because it's quite different from everything we've talked about with qubit systems and so on. So this is section 0. This is like a prologue to the whole tutorial or presentation. So yeah, maybe we can just begin. So yeah, what does bosonic encoding mean? Um, so bosonic, when we say bosonic in the quantum error correction language, it usually just means that we're referring to a simple harmonic oscillator and a quantum simple harmonic oscillator. And if we don't even know what that means, then it's just a system with a very simple Hamiltonian, which is this, where we have a typical kinetic energy term, and then we have a potential energy term, which is just a parabola. This is very similar to the energy of the Hamiltonian in the classical harmonic oscillator also, where the potential is just the parabola right here. But the only difference is the energy levels will be sort of quantized now. And you can already see in this picture that there will be discrete quantum levels, which will be the energy eigenstates. So discrete energy levels, which are labeled by this n equals 0, 1, 2, 3, 4. And I will talk much more about this like in the later part of this tutorial. But okay, so why do we care about these bosonic systems? Why can't we just use qubits? Well, one thing is they occur naturally in a lot of physical systems. For example, we have optical fibers, which naturally allow the simple harmonic oscillator structure. We have these vibrational degrees of freedoms of atoms and molecules. We have microwave cavities, which is one of the like largest platforms for implementing bosonic codes. Then we have other things like these electron light interactions, these mechanical optical resonators. So these are all very different systems, but if you look at the energy levels or we look at the spectrum of these systems, they all turn out to be, to a good approximation, just some simple harmonic oscillators. So if we have reasonably good control over these things, then we can take advantage of the various different kinds of properties these have and encode our quantum information in in these systems. And we'll see some of the advantages in some of the later slides. Okay, so yeah, just to introduce some of the background or like some of the mathematical formalism of how we work with these simple harmonic oscillators. Um, their, their Hilbert space can be labeled in various different kinds of bases, and I'll introduce a lot of them. So first is this position basis, where you can, so this is quite similar to how you would represent a particle in classical physics also, where you just specify the position, where you specify the position of the particle and you say the particle is in this position. That's it. Um, the only difference with classical mechanics, as usually is the case for quantum, is you can't measure the position and the momentum at the same time. So you can either specify it in the position basis or you can either specify it in the momentum basis, but not both. And there's all, yeah, let me just say that. Some properties of these bases is just the position basis is and are eigenstates of the position operator, which are just denoted by these x hats. These are orthogonal or orthogonal in some sense. These are delta orthogonal, which is these properties, and they're also complete. So you can represent any wave function or you can represent any quantum state in terms of the position basis by just expanding it in this form. And the overlap of any state psi with the position with any eigenvector of the position basis, we call that the wave function. These things are not going to be terribly important for our later discussion on error correction, but I thought I should just give an introduction or a background on quantum harmonic oscillators to begin with. Okay, and you can do all of these same things for the momentum basis as well. So they're the eigenstates of the momentum operator. They're also delta orthogonal and they're also complete. Moreover, to switch between these bases, there's this simple function which tells you what the overlap is between an eigenstate of the between an eigenstate of the position operator and the eigenstate of the momentum operator, and this is just this exponential e to the I pi x. What else? Yeah, and this is the this is the thing I mentioned before, is that you cannot measure the position and the momentum at the same time, which means that these two operators do not commute. And this is very famously also known as the Heisenberg's uncertainty relation. This is one of the forms of the Heisenberg's uncertainty relations. Um, yeah, let's leave it there. So this is just to give a sort of general background of how you can go from a classical harmonic oscillator to a quantum harmonic oscillator, and to give some tools to begin working with these systems. Now, for error correction, why do we want to do this? So let's compare the advantages or like the structures of a qubit system versus a bosonic system. So first of all, in qubits, you require a lot of you require multiple systems to encode any sort of information, because a single qubit only has two states. So if you need more states to redundantly encode your information, you need a lot of these qubits, so which requires a lot of these physical systems. So you require, in general, a whole ensemble of these physical systems known as qubits to encode any sort of information. For example, if you have these three qubits, you have a Hilbert phase of dimension 8. Whereas for a harmonic oscillator, it is inherently infinite dimensional. So in principle, you can encode any amount of information with any distance in a single harmonic oscillator. Now, how to control that information and how to manipulate this harmonic oscillator is a whole different challenge. But in principle, you can encode, there's no upper bound on how much information you can encode in a single harmonic oscillator. So what this picture represents is sort of, you need three qubits um, to encode like 8 bits of, or like to have an 8-dimensional Hilbert space, whereas you can easily achieve this with just a single harmonic oscillator. Yeah, and this is all just summarized in this table. For a qubit, you have two basis states. For a bosonic system, you have infinite basis states. Um, Typically, coding would require multiple qubits, but for bosonic, it can all be done in principle in a single mode. We sometimes use multiple modes just to have like better encodings or maybe better control over these modes. But in principle, you can have just one mode. And again, there's no upper bound on the logical dimension or distance of these bosonic codes. Yeah, and there's also this term monolithic codes that was coined a few like recently. This just means that you have, instead of encoding in multiple different subsystems like qubits, you take just one system of a very large dimension or an infinite dimensional large system, and you encode all of your information there. So those are called monolithic codes. Okay, so with that introduction, let's get to the actual presentation where we talk about error correction. So section 1, the Hilbert space and its operators. So I already sort of introduced this Hilbert space of the bosonic systems, but those are not very functional, and we typically don't think of the position and momentum basis when we're thinking of bosonic encodings. We think of different bases, which I will introduce now, and I'll also tell you about some of the operators which are more useful or which are easier to work with. So the most useful and the most intuitive, at least to me, is this fog basis. So what this fog basis is just a change of basis from this position and position or the momentum eigenstates, and you do this by this transformation. So you introduce these other operators called the creation and the annihilation operators. So this is a creation operator, which is just a combination of the position and the momentum. And then you have a dagger, which is called this is the annihilation operator. And we'll see why it's called annihilation operator. And then you can have this creation operator. So this is just a change of basis from these position and momentum operators. But what it gives us is this very simple Hamiltonian. Instead of this p square plus x square, we have this very simple Hamiltonian of just one operator, which is this number operator, this here. So this is linear in this number operator, and essentially all the eigenstates of the Hamiltonian now become the eigenstates of this number operator n. And to label the Hilbert space, this is now much simpler as well. So this can just be labeled by uh, positive integers n, and these states are again the eigenstates of this number operator. So this is another way to represent the same Hilbert space that we represented before with these position and momentum eigenstates. Right. And again, you can write any state psi as a wave function in this number operator, like here. Okay, so let's see how these operators act on our states. So the annihilation operator, um, we'll see the action on these number states, the eigenstates of the number operator. And this has a very simple action of just giving you another eigenstate another eigenstate of the number operator. So if you have a state labeled by n, this just brings you down to a state labeled by n minus 1. And it's also quite intuitive and simple to visualize. So typically we would just represent a harmonic oscillator in this way, where our levels start from n equals 0 to n equals 1, 2, 3, all the way up till infinity. And these all have the same energy gap, which is h mu, or we would typically just say this is 1. We'll work in the units of h mu equals 1. So this is the whole Hilbert space, this ladder of number eigenstates, or the energy eigenstates. And if you want to visualize the action of this annihilation operator, so imagine you were in some state n here, like n equals 4. When we act by an annihilation operator, you just get down here to n equals 3 with some coefficient, which is this square root n, or square root 4 in this case. So it just brings you down one level in this ladder in your Hilbert space. So quite simple. There's a similar action of the creation operator. Let me write this again. So let's try to visualize the creation operator. And maybe you can already guess the action. This just brings you up in this ladder. So this gives you some coefficient plus a state which is labeled n plus 1. So if you start out at some n here, the action of a dagger just brings you up one level. Maybe this is n equals 3, then this is n equals 4. So quite simple. This another way to visualize these operators, and this will sort of relate to why these are called annihilation creation operators and why these are bosonic states, is if we imagine that we have some cavity or a fiber which has some number of photons, then sort of what this annihilation operator does is it removes one photon from the system. So now you have one less photon or one less quanta of energy. And in this way, it annihilates a photon, right? It annihilates a boson, which is a quanta of energy. And in the similar way, the creation operator does the opposite thing, which is it will create another guy, this guy right here. So if you had, let's say, 7 quanta of energy here, now you have 6 here, and you had 5 quanta of energy here, you have 6 quanta of energy here. And these quanta of energy is like interchangeably called bosons or photons. Um, yeah, and bosons, again, like if you're familiar with that language, it just means that you can have multiple of the, like, you can have identical states in the same system, and that is allowed. So as opposed to fermions, where you cannot have two identical states in the same system, they annihilate each other. In bosons, you can stack multiple states, which are multiple identical states in the same like waveguide or cavity or the same system. Yeah, so that's why they're called bosons, and that's why these are called annihilation and creation operators. Okay, let's now go to section 2. So now we can start talking about quantum error correction and like what kind of errors these systems have and how we can correct against them. So I actually think my presentation is going to be quite small, but these are a lot of new concepts, so I thought I'll keep it small and maybe just introduce one code today. Let's see how it goes. Okay, so let's compare the noise model in these bosonic codes with the noise model that we had in the qubit world. So in qubits, we had these Pauli X errors. So for a two-level system, the Pauli X, what it did was it brought this state to here and it brought this state to here. So it just swapped the two states in between. It just swapped the two states that we have that we labeled by 0 and 1 typically. The analog of that when we're thinking of the Fock states is this photon loss error. So let's draw this Hilbert space again. And what this photon loss error does is it's just the operator A to a good approximation. So if you have any state here, it will go down here. If you have any state here, it will go down here, and so on. So that's what a photon loss error is. And I call it sort of the analog of the poly X because it's bringing some transition between the different states of your Hilbert space, which is in contrast to this poly Z error, where the action is just some phase in the state. So if you had a zero state, then it gave you the same identical state. And if you had a one state, then it gave you the negative of the original state. So it just gave you some phase on your computational basis or your basis states. The analog of that in the bosonic language is this dephasing error. So this is just the number operator. And what it does is it gives you not exactly a phase, but some coefficient. So it interferes with the coherence which you might have in different states. For example, like if you had a state, let's say 2 plus 4 plus square root of 5 with some normalization, and you applied the number operator on it. So you can see that there's an equal contribution from the 2 and the 4 state and some different contribution from the 5 state here. Then this thing will go to 2 plus 4 plus 5, again up to some normalization and prime. So sorry for the sloppy writing, but what it did, it shifted the balance between how much these different states contributed. So it can interfere with the coherences that you had in your initial state and move it to, and it's a completely different state essentially by introducing some phases effectively. Okay, so that's the analog of the Pauli errors in the Fock states, and we can also think of a vague analog of the multi-qubit Pauli X's and Pauli Z's. So if you had an m-qubit Pauli X error, then the probability of that would go like p naught to the power m, where p naught is the probability of this error happening on any one qubit. And similarly for the for the z errors, multi-qubit z errors, the analog of that in the bosonic language would be this m photon loss error, which is represented by a to the m. So what it does is instead of bringing you down one level, it will take any Fock state and bring you down m levels. So here I'm representing m equals 2. So a second order photon loss would bring you down two levels directly instead of bringing you down one level. And similarly, an mth order, we write it in black, an mth order dephasing error, which is just represented by this thing. It yeah, it's an mth order error of the same kind. So the action again is very simple. It's just it's just a photon number exponentiated by m. So this is a much harder error to correct. This is a harder error to correct with because the order is different, or the order is higher, and again the probability of these things would grow exponentially or well, decay exponentially with n. So this is sort of the analog of multi-qubit Pauli errors in the bosonic world. And these are the two major sources of error that we're going to work with in the bosonic error correction, which is photon loss and dephasing. Now we can introduce our first code. This is, in my opinion, the simplest bosonic code. People might disagree, but I think it's quite simple. So you have two logical states. We're trying to encode a qubit into a bosonic mode. So in this infinite dimensional Hilbert space, we're trying to encode two logical states. And we'll see how this works and how this can actually correct against the photon loss and the dephasing errors that we talked about in the previous slide. So our zero state is just this zero, a superposition of this 0 and 4, and one state is just the two state. So let's represent this 2, n equals 3, and n equals 4. So the zero state is just comprised of an equal superposition of this guy and this guy. And the one state is just this guy, standalone. Now, how this works, let's see how it can correct loss errors. So loss errors. And my claim is that this sort of encoding can protect against up to one loss error. So the action of loss error on the logical states, we can easily write down as this 4 and sorry 3, and all of this contribution comes from this guy because zero state is just annihilated. So if you just try to see the action from the formula, a star of 0 would just be 0 times -1. So like this is non-physical and this is a 0 anyway. So this is just 0, not the state 0, but just the state is completely annihilated. So there's no contribution from this guy when we apply the photon loss error. Okay, if on the one state, we can write down the action as just square root of 2 times 2, 1. And this is actually the square root of 2 times 3. Yeah. So what's the action in this Hilbert space? On the zero state, we are brought down to here, and this just goes to the vacuum, or not the vacuum, sorry. It's just annihilated. And this state is brought down to n equals 1. So these are the erroneous states that we have. Now, how do we correct against these? Or what is the analog of, let's say, I'm going to copy this. Oh, we already have it. Again. Yeah. So the way to correct against this is, again, similar to how we do it in the qubit world, where we measure some syndrome. And the syndrome in this case is quite simple. So if we carefully try to observe these states, 0, 4, and 2, all of these are even photon number states. And these 3, 1, these are all odd photon number states. So the logical states are completely supported only with the even photon numbers, and the erroneous states are only in the odd photon numbers. So as a syndrome, we can just measure whether a state has an even parity or an odd parity, and that will be our syndrome measurement. If it's in even parity, then we can say that nothing happened, the error was identity. And if it's an odd parity, so if the parity is even, then the error is identity, which is no error at all. And if the parity is odd, then we can say that there was one photon loss error. This is simple to represent in an operator form, which is just this. So you take -1 and exponentiate it with n hat. So the action of this is again -1 if or if n is equal to odd, and 1 if n equals to even. So if we are somehow able to measure this operator, then we can measure the parity of our system and we can determine which error happened or if an error happened at all. So if it's even, there's no error, and if it's odd, then it's a loss error. Yeah. So this is the way to do a syndrome measurement for this binomial code. And once we determine what the error was, we can sort of reverse it. We can recover our original information back. So yeah, the claim was that it can correct up to one loss error. I still haven't proved actually that it can correct one loss error. I've just told you that there's a syndrome which can determine which error happened. To prove that it can correct this error, we will look at the nil-Flam conditions. And if you don't remember what this was, I'm sure this was introduced before, but these are just a set of conditions. I imagine them as two sets of conditions, which is this and this. But if your code space and your error model satisfies these conditions, then there is guaranteed to be some sort of decoding procedure and syndrome measurement which can correct the errors exactly. So I mentioned these in two sets, and the intuition behind this is there are these off-diagonal conditions, which intuitively just means that if you have some orthogonal logical states, then they will remain orthogonal even after the action of the error. And then so like the errors cannot ever create some overlap between orthogonal logical states. And then there's this other set of conditions, which are these diagonal conditions. And this intuitively just says that the error model or any error operator cannot distinguish between any two different states of your logical space. And these two are necessary and sufficient for error correction to be successful, just in an intuitive way. So, okay, let's see how this binomial code can satisfy these nil-Flam conditions. My claim was that it can correct errors up to one photon loss. So then this error set is just I and A, which is the no error identity and one photon loss A. So E, A, and EB in these conditions, in these nil-Flam conditions, are going to be taken from this set. So we can check each of these conditions one by one. Let's check the off-diagonal conditions first. Um, let's look at this guy. I1. This is 0 because if we look at it, then the 0 and the 1 state, they don't have any overlap. So the 0 and 4 it is supported by the 0 state is supported by the 0 and 4 Fock states, and the 1 state is supported by the Fock state number 2. So the overlap of 0 with 2 is 0, and the overlap of 4 with 2 is 0. So this condition is satisfied. Then we have this guy. So for this, we will look at the overlap of this with this state. And again, they have different they have different Fock numbers. So this overlap is also 0. Let's look at this guy. And I did not write down a dagger 1, but it's simple to write down, so we can do that. This is just going to be square root of 3 times 3. I've just applied the creation operator here to this state here. And again, then we can look at the overlap of this with the 0 logical state, where the overlap again is 0. So this again is 0. And the final condition would be a dagger A1, which is nothing but the n hat operator. And the n hat operator doesn't change the Fock number at all. So this overlap is also going to be 0 for the same reason that this condition was 0. So we see that all of these, oh yeah, and like the conditions of this form are just like complex conjugates of the other guys. So this is also automatically 0. So all of these off-diagonal conditions are satisfied, all of these off-diagonal Lindblom conditions. Um, then the other thing to check would be the on-diagonal conditions, which is the second set of conditions. This is also easy to do, where we have the same logical states on either end of this sandwich. First would be this guy, so we will look at the overlap of A0 logical with 0 logical. Again, there's 3 here and 0, 4 here, so there's no overlap. This is 0, and this has to be equal to 1, the same overlap, the same expression for the one logical state. And this is again also easy to see by checking the overlap of this with this, where you have a Fock state number 1 and Fock state number 2 here. So this overlap is also 0. So we have this condition 1, and we need to check this. For this, we can, maybe I'll write this down again. Equals root 3, 3, and equals 1 plus square root 5 over square root 2, 5. And these are both again going to be 0 because we have changed the photon, this Fock number by 1 by applying this operator. and these are the resultant fork number is never going to be equal to the same fork number that we started with because we have changed it by 1. So the overlap of this with this is 0 and this with this is 0. So these are both 0 and this is satisfied. And yeah, I think that's maybe enough and we don't need to check the rest of them, but I will just mention what these conditions are, the rest of them. So maybe we can check, like if people are interested, they can check this on their own. This is going to be 2, and yeah. This tells us that these diagonal Navier-Laflamme conditions are also satisfied, and so all of these quantum error correction conditions are satisfied by this simple binomial code. So this code is guaranteed to work. Yeah, and that is our simplest Bosonic code that we can think of, which just requires these 5 Fock states, and it can encode a single qubit of information with a distance of 1 in this photon loss, distance of 3 in this photon loss error, because it can correct up to 1. Right. Okay, so that was the simplest binomial code, but in general, we have this whole family of binomial code. Let's use this. We have this whole family of binomial codes where you can correct any amount of information and have any distance that you want. There's something in the chat. The one that talk. Okay, I'll reply to this later. Yeah, so there's a whole family called binomial codes. I forgot to put the citation here. Maybe I'll send it in the Discord later. But yeah, so given any amount of losses that you want to correct and any amount of dephasing that you want to correct, you can create a binomial code in this way. And this is a very deterministic recipe. You can just write down, like I have written down these expressions exactly. Um, so this is, let's maybe break this down a little bit. This is just some normalization. Then you have these binomial coefficients. N plus 1, the simple just means n plus 1 choose p. And because we have these binomial coefficients, these are called binomial codes. And then you have these Fock states where the number of losses that you want to correct, these dictate the spacing between the different levels that support one logical state. So for example, if you wanted to correct just one loss, as in the previous code, you had a spacing of 2. Like we had a spacing of yeah, we had a spacing of 2 between these different states of the logical space. If you wanted to correct more loss errors, then we would have a larger spacing. And yeah, so the different code words are just built by taking these states which are spaced out by this number of losses errors plus 1 with these coefficients. But you also separate them out. You take sort of a partition between these Fock states which are separated. So all the alternate states are in one code state. So for this p equals even, we have the one logical state, and p equals odd, we have other logical state, which just means that if you have these states like separated by these L plus ones, no, this is not L plus 1. L plus 1 is, oof, I cannot erase. This is 2 times L plus 1. Anyway, so yeah, if you figured out which states you want in the system, then you just take alternate states to form one logical state and the other remaining states as your other logical state. And that's sort of the support of the code space, and then you can just put the square roots of the binomial coefficients. And the claim is that again this code can correct up to L loss errors, so up to operators of this form, and correctable dephasing order, I guess, is D. So it can correct up to this dephasing also. So instead of like trying to think of instead of like having a code space and trying to figure out how many losses and dephasing it can correct, it's easier to start out with the parameters that you want, to start out with this L and D, and then choose and then construct your code words in a way that they can correct against the amount of errors you want. So if you decide on an L and a D, then N is deterministic, and you have already determined N, and you can form this code space. Okay, let's do another example just to see how this recipe works. So instead of correcting against one loss only, we will now construct a code which can correct up to two losses and also one dephasing error. So let's write down what the states would look like. So the first factor was, okay, maybe even before this, let's compute what n is. So L is equal to 2 here, D equals 1, and n was max of L and 2D. So this is just going to be max of 2 comma 2, which is 2, right? So the zero code state is now, we have the expression here. So I'm just gonna plug in the numbers. Square root of 4 times, then the sum of p equals 0 or p equals 0 to 3, which is n plus 1, but only the odd guys. And square root of n plus 1, which is 3, 0 with the 0 state, plus square root of 3, 2 with the 2 state. Wait, is that right? No, 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 no. This is the 0 state, and then we have 2 times 2, 3. This is L plus 1, so 2 times 3. This just turns out to be 1 over 2 times the 0 state plus this is square root of 3 times 6. So that's the 0 logical state. And then the 1 logical state is just going to be this thing. I'm not gonna, oh, I don't need to write this down actually. It's going to be 3 choose 1 with 3 plus 3 choose 3 with 9. So this is just square root of 3 times 3 plus 9. So this, I claim, is a binomial code, is a quantum error correcting code, which can correct up to 2 losses and 1 dephasing. Just to demonstrate it with the Hilbert space also, let's put this here. So we need 9 levels, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 levels because we have 0 also. 3, 4, 5, 6, 7, 8, 9. The 0 logical state is supported by the 9th state, and the 3rd state. And we see the spacing is of 6, which is equal to 2 times L plus 1. And then we have this other logical state 1, which is the superposition of 0 and 6. And it's also intuitive to see how it can correct up to 2 losses, because one loss will bring it here and another will bring it here, and it still doesn't overlap with the other logical state. So the number of losses you want to correct really dictates how spaced apart you want these states these fork numbers to be. If you wanted more loss errors, you would separate it out even more, of course. Yeah, so just to make it even more concrete, the error model would be this. It can correct this guy, and this guy. So 1 dephasing and up to 2 losses. We can also try to think of the syndrome measurement for this. So similar to the parity for the first binomial code we looked at, in this thing we can measure the parity, or not the parity, but we can measure the fork number mod 3. And this will tell us which error space we are in. So if this is equal to 0, then this is the identity error. If this is 1, then we have a single photon loss, and this, if this is 2, then we have 2 photon losses occurring in our system. Actually, I think this is -1 and -2. Yeah, -1 and -2 actually. Write it down. 0 is the identity, -1 is the, and -2 is 2 photon losses. So in this way, we can determine the syndrome of the error for this particular code. Okay, maybe I'll cover the coherent states actually in the later section, but I don't know. Can we have questions, Kishore, or we're just going to have it on text? So that's essentially all I wanted to say in the first tutorial.
I mean, if you want to take questions, we can take some. Yeah.
Yeah,
Maybe people. I mean, by the way, it was very, I would say, yeah, like I mean, very pedagogical. Thanks, Shubham. Yeah. So people can ask questions if someone wants. People have it.
yeah, I'm happy to take questions because there was a lot of content in this and like a lot of new content. So maybe you can take some questions here, and then of course I can answer on Discord. So if people want to put it in the chat or just unmute themselves, I'm happy to answer.
So Shubham, right. So sorry. I got one small question. So about this binomial code, like can you verify it by checking the neural Laplace condition? Like for example, here you have this like your error state is this for like the a and a square and this n. Like how can we
This,
verify this by checking this neural Laplace condition?
yeah, so it's a good question. You can of course verify this by checking the Nilaflam conditions. The only thing is that there's going to be a lot more of these conditions to check because you have more operators now. So actually, let me see where I can write it down. I think I can insert a new page. Sorry. Okay. No, okay, I'll just erase some of this. So before, when we had just I and A errors, like yeah, when we had only the I and A errors, we had essentially 4 conditions to check for each of the off diagonal and diagonal ones. But now what you will need to do is you will need to check it for A, like all of these guys, plus all the combinations of these things. So you would need to do, well, this is already covered by N, but you would need to do it for, let's say, this guy. You would need to do it for a dagger square A. You would need to do it for a dagger square N. You would need to do it for A squared, a dagger N. You would also need to do it for N squared and A squared and so on. So there's a lot more of these conditions, but you can of course do this. And by just plugging it in, by just plugging the values of the, or like plugging those operators and these states into these conditions. And these off diagonals ones are sort of easy to check because essentially what they do is they take any logical state and they apply these photon loss errors. So it will only, so the resultant states are essentially either this or this, I mean, for all of these things, and you will see that they never overlap with any of these other states. So the off-diagonal ones are sort of automatically satisfied when you choose this spacing of L+1. For checking the dephasing conditions, you actually need to compute these things, and that's a little bit more tedious, but all of the Nil-Laflamme conditions hold. And if you're like feeling even more rigorous, then you can just take the general form of these binomial codes like this, and you can plug in the Nil-Laflamme conditions, all of the Nil-Laflamme conditions for all the errors up to loss errors and L and dephasing error D. And you will see that all of them are satisfied because of the special structure that these binomial coefficients have. So the off diagonals will be satisfied just because of the spacing, and on the diagonal conditions where the overlaps are not zero will be satisfied because the averages of these binomial coefficients are all the same for the two states. Hope that makes sense.
Thanks. Yeah. No, I see it.
There's something else in the chat. So binomial code is not fault tolerant for arbitrary errors. Example doesn't correct displacement errors. Yeah, so it's a different error model. You would not want to use binomial codes if you want to correct these displacement errors. There's other things for that. For example, these GKP codes that I'll talk about in some of the later sections. But yeah, it depends on what kind of error model you want to select. So I would say binomial code is not a great selection if you want, if you are dealing with something like a displacement error model. Um, yeah.
So here
Uh,
you demonstrated how the syndrome measurement tells you about loss errors.
Mhm.
What about the dephasing error?
Yeah, so the dephasing error is different. You cannot do the same syndrome measurement for the dephasing errors. And how can you measure dephasing? I'm not exactly sure. So that's why we check these neural flams is they guarantee you that there is some decoding procedure, but off the top of my head, I don't know if this is done actively. I mean, so in a lot of these cases for the bosonic codes, you can do something called passive error correction or autonomous error correction, where you don't actively measure syndromes, but you put your system in some environment where where the states that you get, like the environment takes care that you always end up inside the logical code space. So I think maybe the dephasing errors are corrected in that way, but I can check and get back to you on that. I'm not exactly sure at the moment.
Thank you.
But yes, the same syndrome measurement would not work.
Thanks.
can I have one more question here?
Hmm.
So suppose we have like both single photon loss and dephasing. Is it possible like to correct both of them? Like
Yeah,
I
no,
mean,
for this
n-
code, no, because it will be a different
okay,
order error. And if it was possible, yeah, we would have put some more, yeah, we would have put another operator in here. So yeah, I don't think it's possible to correct both of them at the same time with this code.
okay, okay.
Shubham, I have like very, I would say kind of, I don't know, maybe people have already worked on it, but but I mean, kind of think of, like the first binomial code that you presented, that's very classical in nature. Like, I mean, in the sense that it's a bit more like a repetition code kind of, I would say, like it just protect against like, single kind of error.
Hmm.
Uh, and if you think that's the case, then I was wondering, if people have thought of trying to understand these via like some kind of in the chain complex language, and then maybe you take like some hypergraph product of two such uh, binomial codes, and that will give you like a bosonic version of I don't know, like a tori code. It should give you bosonic version of tori code if you start with, let's say, such binomial codes like the simplest one, and then if you take the more exotic ones, I don't know, you may get some other interesting hypergraph product code. I mean, I don't know whether this question even makes sense, but I'm thinking whether, like whether we can put them on some in chain complex language and then borrow all the idea of, like the products and twists that we have in the, like in the like in the qubit world or qubit world, and bring it here in the bosonic world.
Right, yeah, I mean, the interesting, I think I don't understand the hypergraph product construction in enough detail, but I can say that maybe something similar is you're probably familiar with like these concatenations of bosonic code with qubit codes, like the surface code. So that seems to me like something similar. Like typically you would take something like a two-legged cat code, which again I'll talk about in the later sections, but two-legged cat code, it also corrects against only one kind of error, so it's also classical in that sense. And then you put concatenate it with a large surface code or something, so that the surface code can correct against one kind of error and the cat can correct against the other kind. So you have both protections, but maybe that's like much more simple than the hypergraph construction you're imagining. Like to my knowledge, I don't think anybody has looked at putting it in that language, but I don't know how that would work, but maybe it's an
Yeah,
interesting direction.
yeah, because there the topological thing has become quite advanced, like I mean,
Yeah,
and
it's
and I
yeah.
think some basic things, like maybe one can do here, and like if not, people have not looked at, and then try
Yeah.
to do analogous things.
Yeah, I don't think people have looked at like hypergraph product constructions of purely bosonic codes. So maybe there is something there, but yeah, I would need to understand these things better to say more concretely.
Thanks.
But nice, interesting.
Any other questions here? Okay, so maybe we end here. Like, thank you for your listening, and thank you, Shubham. It's a very pedagogical talk, very interesting. Okay, see you
Yes,
next week,
thanks a
guys.
lot. Bye.
Thank you. See you guys.